So I'm going to talk about a joint work with my collaborators, Shuang Miao and Saurabh. He is currently a professor in Wuhan University, China, and Saurabh Shashahani. And he's now at University of UMass Amherst. Okay, so here's the outline. So I will first introduce the model. So I will explain the general framework to study ideal fluids in relativistic framework. And then I will introduce the so-called hard phase model. And we are interested in a free boundary problem for this hard phase model. So what we have been able to do is proving a well-posedness result. So this is, of course, a local well-posedness, local in time. And of course, the main step is to finding the a priori estimates, okay? And of course, then construct solution becomes quite natural once we find the a priori estimate for our model. And then it turns out that our estimates is also very robust. It can actually apply to, actually it's already give a uniform estimate, and that allows us to pass to the Newtonian limit as the light speed of light goes to infinity. Okay. So here is, so we know what's we have a fixed background, right? So that with Minkowski metric given by this standard form, okay, -1 in the time, and then identity matrix in the space. And we will denote that upper and the lower with upper and the lower, right? So the Greek letter upper and lower corresponding to M and the M inverse, okay? And we have 4 dimension, the first 0 corresponding to time. But a lot of times we really just write time, okay? T, not just x0, okay? Okay, so we know that if we want to describe a fluid, we need to introduce the velocity field, okay? So in the relativistic setting, the velocity field is a future-directed unit time-like 4 vector, okay? We use this notation, and being unit means this, and the future-directed, okay? So yes, U0 is positive. The time component is positive, okay? Okay, so now we need some additional quantities to describe the fluid motion, right? So N is the number density of the particles, and P is the pressure, and rho is density, energy density, S the entropy per particle, and theta is temperature. And we know from the law of thermodynamics that the energy density and the pressure has to be non-negative, and they also have to satisfy these relations. Okay, so P is N, the number density, times d rho dN minus rho, and the theta is 1 over N, the temperature 1 over N dP ds. Okay, so that's the general thermodynamics, law of thermodynamics. And the sound speed is defined as dP d rho, okay, relative to the entropy. Okay, so this is relative to the entropy. And we know, and then we want to actually choose appropriate units so that the speed of light is 1. Okay, so the speed of light is 1. Okay, the speed of light is 1. Okay, and then sound speed should be no more than the light speed, right? Speed of light. So it's between 0 and 1. Okay. Okay, so we know that the fluid would satisfy conservation laws, right? So at first, it's a conservation of energy momentum. So the energy and momentum tensor is given by this formula, okay, P plus rho, okay, UU, M plus PM. This is the particle current is given by the number density times the velocity, okay. And we also have that the conservation of the particle current, okay. And in fact, we are going to restrict ourselves to the study of barotropic fluid. Okay, so by being barotropic means that the pressure should be a function of the energy density. Okay, and we assume that this function is strictly positive. Okay, by writing strictly positive, then we can define this quantity F, capital F is integral from 0 to P. So P is a function of rho. Okay, so we introduce a new quantity, which is dP divided by rho plus P. And we introduce a new vector field. Okay, so this vector, the fluid velocity times e to the f. Okay, so e to the f, this is the length of this vector. Okay, and of course, this is trivial that the length square should be just given by that. Okay, that's a formula. Okay, so this means that f is also a function of p, right? Or in other words, p and the rho is a function of f. Okay, or p and the rho is a function of this length of v. Okay, okay, so this equation, so by just doing this, remarkably, the equation of the motion becomes these two. Okay, so this looks like a lot better than originally, right? So originally there's the energy momentum tensor, right? So it looks pretty complicated if you look at this equation. Okay, but after this introduce of this new variable, okay, and becomes much easier to understand. Okay, so okay, so the first equation here is corresponding to the conservation of the energy momentum, and the second one is conservation of the particle current. Okay, so now this function g is derived to be satisfy this. Okay, so in fact, this is really easy to check. And the derivation of this we find in the paper of Christodoulou of 95. Okay, so this equation 2 is very important. Okay, it's very important for us. Okay, okay, so now this in general describes a barotropic fluid, right? So that's the equation. Okay, okay, so now we want to even introduce more simplifications. Okay, and we assume that the fluid is irrotational. Okay, so irrotational is usual, right? So that means the velocity field equal to the gradient of some potential function v. Okay, and we assume that. So this is actually a assumption. Okay, so we assume that some speed equal to the speed of light. Okay, so a lot of people probably have already started to doubt why anybody want to study such a model, right? The sound speed cannot equal to the speed of light. It should be strictly less. Okay, but it turns out that this hard phase model is one of the well-studied, mostly studied model in the general relativity. Okay, so a lot of times, so this have a name. This fluid is called stiff or incompressible, if you assume that the sound speed equal to the speed of light. Okay, so now in this case. Well, this is actually derived in the paper of Christodoulou. So you can plug in, because dP d rho equals to 1, you can just calculate, and P is half of length of V square. Rho is half of length V square plus 1, minus 1, 1 plus 1. And this quantity G is just identically equals to 1. Okay. And this is, for the sake of curiosity, that's the energy momentum tensor and the particle current just follow this formula. And now this quantity V in the hard phase case is actually the enthalpy. Okay, so in this case, in the hard phase model, V is enthalpy. So now we are interested in the hard phase model with free boundary. So in other words, so we want to say that, okay, so initially so we are given a space-time domain, right? And assume that boundary of omega is time-like boundary of omega. So what does that mean? So time-like boundary means that, okay, so this is our fluid domain. Okay, so our fluid domain. So this is initial domain time, and the time-like boundary, right? So this whole domain, sorry, okay. So this whole domain is omega. Okay, this whole domain is omega, and the time-like boundary is only this part. Okay, so okay, it doesn't include the top and the bottom. Okay, so this is the omega. Okay, so this is the time direction. Okay. Okay. So the time-like boundary is only, this part. Okay. Okay, so now, oops, I think I added a page in the wrong place. Okay. Okay, so we assume that, okay, so the free boundary problem is the following. So we assume that the fluid has sound speed equal to the speed of light. So this is the equation of energy momentum, right? Okay, and the conservation of energy momentum, and this is precisely, this is because the number density, this is actually V mu is really the number density. So this is conservation of the particle current. Okay, and then this is our just notation. Okay, you can just forget about this. This is like irrotation. Okay, so this is like D is a exterior one form. Okay, and then so we have that the pressure. We assume the pressure is 0 on the time-like boundary. Okay, so of course because pressure. So we assume that the pressure is greater than 1 on the boundary, equals to 0, greater than 0 in the interior of the domain, okay, of the fluid domain. Okay, so that means there's no bubble inside. Okay, so because sigma square minus 1. Okay, so let's see. Yeah, so sigma square. So this is sigma square, right? So P is really equals to half of sigma square minus 1. So in other words, we assume pressure is 0 on the boundary and the pressure is positive in the interior of the domain. Okay, and we also assume that the velocity field is tangent to the boundary, the time-like boundary. So in other words, this is equivalent to saying that the particle was on the boundary, stayed on the boundary for all time. Okay, so the fluid is a barotropic fluid, and we assume we assume it's irrotational. And in fact, this condition looks very much like the incompressible, right? So it's incompressible or stiff, okay? And we also assume that the particle moves along the boundary, was on the boundary, stay on the boundary, okay? Now we also make some assumptions on the data, right? So we assume that initially the pressure, the fluid, occupy the whole domain. Okay, so there's no bubble inside. So in other words, the pressure is strictly greater than 0 inside. In fact, we assume more than that. Okay, so and you can see why. So for anybody study Waterway, in fact, we need this assumption. Okay, we need this assumption. Okay, not just the one in. So of course, the first assumption is consistent with the second, right? But stronger. So in other words, the pressure is strictly increasing along the boundary. Okay. So the pressure is increasing in the inward normal direction. Okay. 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 So basically, the result can be stated simply. Just suppose you start with something sufficiently smooth. Okay. Suppose say has finite many. Sorbonne norm is finite. Okay. And of course, assume that the data satisfy the equation at initial time. Okay, so then it will lead to a unique solution for a positive time period. Okay, so in other words, say starting with initial fluid occupying this domain omega 0, and then you can just continue for a while with this free boundary problem. Okay, and this time is quite short. Okay, so for some positive time 0t. Okay, and of course so this is a remark. Okay, so this condition on initial data is the relativistic Taylor sign condition. Okay, so this, in other words, this condition. Okay, so this particular condition is a Taylor sign condition. Okay. Okay. Okay, so, and of course, we don't really try to prove a very low regularity result, right? Because, so we're not making effort to make the statement how little regularity is required at initial time, okay. Okay, so why this fluid model is relevant? Okay, so in fact, so if you look at relativity GR literature, and there's a description say that, well, during the gravitational collapse of degenerate core of a massive star, and in general, it's thought that the sound speed is thought to approach the speed of light. It's pretty close, okay? So you can find these in these literatures, okay? And then the half-phase model is an idealized fluid for this physical situation. But of course, we choose this model for some other reason, right? So we don't want to start with something very too general to get straight away from other difficulties, okay? So in fact, the half-phase models, it's similar to the Waterway, right? So most of the time we study incompressible, irrotational, because it actually captures the main difficulties of a class of free boundary problems. So in fact, our approach applies to the general barotropic fluids, okay, with non-zero vorticity. Vorticity will not pose difficulty here, okay, and you can see that this approach also works for the general model, barotropic fluids, okay. And in fact, after working this out, we realized that in fact, this general approach should work for a wide variety of free boundary problems. For example, it can also be used to study the compressible fluid, okay, but that will be a separate topic. Okay, so different from the water wave model, the Newtonian case, in fact, we don't really find a lot of results for the relativistic models, okay? So for the gastro model, so this is a different type of boundary condition. This is a free boundary condition, okay? And so Makino, Reno, construct a class of solutions, okay? So existence of class solutions, okay? So existence of class of solution, and then Hazik, Scholar spec, okay? And also Juhi-Jan, Philip LeBlanc, okay? Nada Masmoudi, and they obtained a Pauli estimate for the gastros model, okay? And Trickeny proved existence for this gastro model using Nash Moser iteration, okay? But our model in general is called liquid model, okay? So what's more close to us is really these two work, okay? So the work I'm going to describe is called liquid models, the liquid boundary, free boundary, okay? So Olinik, in a series of paper, actually studied the existence of this model but using a very different method, okay? So he wrote like 3 papers, 3 very long papers. Shortly speaking, I can say that, well, his method can be said that propagate. So in fact, we don't understand. I don't understand, okay? So forgive me if I say it wrong. So it's really like propagating of constraints, okay? And then, so he got existence of the solution under some constraints of the initial data, okay? Now Ginsberg what Ginsberg did is he proved an a priori estimate for the same model, but with a smallness assumption. So this smallness assumption basically says that he can perturb the Newtonian model by a little bit. Okay, so his method is really much based on the Newtonian, and he did a perturbation, so he can find a priori estimate. So our result does not require any smallness, okay, and okay. So, and we also have the existence and well-posedness, okay, and also, okay. Okay, so maybe I should, so the question is really that, I mean, as usual with all the free boundary problem is really that where do we start, right? So how do we study this kind of problem, okay? So this is very useful to let me just recall the Waterway problem, okay? So we actually, because we don't really know how to start with this, so let's just recall what's a Waterway problem, okay? So remember the Waterway problem, and as usual, also that so this is a Waterway problem, and it goes to gravity, okay? And divergence equals 0, curl equals to 0, right? So this is fluid domain and the fluid domain, and we assume that the pressure equal to 0 on the boundary of the fluid, and also the particle moves was on the boundary of the fluid domain, remain on the boundary. So we also have this 1v is parallel to the boundary of omega. Okay. So similar, very similar looking, right? So, and you can see this is actually very similar looking from this one. Okay, so now we have a free boundary. So the method of studying water waves, so let me just describe the 2D case, right? So in general, this is a well-used method is just to reduce the problem on the boundary. Okay, so reduce problem on the boundary. So if z equal to z alpha t is the interface, so this is omega t, right? So this is the boundary. So this is the boundary of the fluid domain, and you just describe using Lagrangian coordinates. Okay, so this means that if I take one derivative, I get velocity. I take 2 times derivative, I get acceleration. Okay, and if you notice that this is acceleration, right? So we just write the equation on the boundary. Okay, so the acceleration, I just circled it. Okay, let me just squeeze a little bit. Okay, so this is really just, so we can write ztt, and the gravity, okay, so if we use complex variables, so g is 0 minus 1, so this equal to just minus I, so we move the gravity to the left-hand side and move the gradient p to the right-hand side, okay. But we also know grade p equal to 0 on the boundary. P equals 0 on the boundary means gradient p is perpendicular to the fluid boundary, right? So we just, right, we can just, and we know that, okay, so this is a tangential direction, right? Taking derivative to the parameter, and I z alpha is a normal direction. So if you just decompose gradient p along the normal direction, tangential direction, only the normal direction survives, okay, and n. So then if you write and replace dp dn, okay, so this is n is I z alpha divided by z alpha, okay. And we can just write this as minus dp dn times 1 over z alpha, okay, I z alpha. And you can just write, so this is something I have been using all the time is I write IA z alpha, okay. So A is precisely minus dp dn 1 over z alpha, okay. Okay, so now it turns out, of course, we have already had quite a lot of times to study waterway, okay. It turns out that, okay, so also that we know that ZT is the velocity field, so that means the boundary value of the velocity field, and we know the velocity being incompressible, irrotational means it's its complex conjugate is holomorphic, okay. And using complex analysis, the Cauchy integral formula, and you can write it as that's equals to Hilbert transform acting on ZT bar. Okay. So the Hilbert transform, just let me just define it here. Okay, 1 over pi I. So this is like twice of the Cauchy integral. Okay, so that's Z alpha t minus Z beta t, and this is Z beta. Okay, and then acting on ZT, right? So I'm writing like ZT beta. Okay, so D beta. Okay, so that's how it's read. Okay. Okay, so this is a Hilbert transform. So I should probably really write it separately. So instead of writing this. Okay. So let me just erase that. Okay, so the Hilbert transform is defined to be, okay, is that acting on a general function f, okay, is f beta, d beta. Okay, so that's the Hilbert transform, and that's the principal value. Okay. Okay, so we have a system on the boundary, right? So it turns out that in the work of 99, that we have shown that after taking one derivative to this equation, okay, so this equation is ZTT plus I equal to IA Z alpha, right? If you just take one material derivative. Okay, so if you take one material derivative to this equation, and you get a quasi-linear equation. Okay, so if I take one material derivative, right, so this is equal to IA ZT alpha plus I AT Z alpha. Okay, so we move one term to the left. Okay, and these two terms will be the higher order terms. Okay, so these two terms will be the higher order terms, and the right hand side the lower order terms. So why this is true? Okay, so let me just put a bar on all the terms. Okay, and A is real valued, right? Okay, so why that? This is the left hand side is higher order term. Okay, higher order term. Okay, higher order terms, and the right hand side is a lower order term. So why is this? And roughly you can think as the following. Okay, so this is really like the left hand side is two material derivative. So because we are in Lagrangian coordinates, right? So this is material derivative and plus IA, the alpha, acting on the velocity field on the boundary, okay, equal to that. Okay. So roughly speaking, you can think the left-hand side is a derivative of holomorphic function, okay? And the right-hand side is just pointing in the normal direction, right? Because if you look at here, this is not, because AT is real valued, IZ alpha is normal. So this is just strictly pointing in the normal direction. And a holomorphic function, if the tangential direction equal to 0 on the boundary, then the whole thing just equal to a constant. Okay. Yes? Any question? Okay. So, but of course, the left-hand side is not holomorphic. So that means the right-hand side is not 0, but it's a lower order term. And the being lower order can be checked by just applying I minus H. Remember, being holomorphic means I minus H acting on this equal to 0. So acting I minus H to both sides, you can find a formula for ZT, and then you will see this is lower order. Okay. So, okay. And equal to, I will not, then you get a commutator, right? On the left-hand side. Okay, so now let me, so of course that's what we do in general. A lot of, most of time in Waterway, if you look at the literature, so a lot of, there are many different methods we have already seen in this conference, right? But most of time we really just study the problem on the boundary. But it was Limbara, okay, so this paper of Limbara, okay. In 2000, okay, so they want to study the Waterway problem, not really Waterway, right? A free boundary problem, but Newtonian version, and with non-zero vorticity. So this becomes complicated if you look at the boundary, okay? So, but they realize that this equation just taking one material derivative, so this is obtained by taking one material derivative to the Euler equation, right? And restricted to the boundary. So we can, so this is exactly how this is obtained. So you just take, so you look at Euler equation, you write this as material, this is a material derivative. Okay, so this is a material derivative. And we write Euler equation like this, okay, equal to the gravity. So what we actually have done is really, we just took one material derivative to the Euler equation. Okay, so I'm just writing this, okay, dt gradient p equal to 0, right? Because gravity is 0. And if you look at carefully, so that's we can just write this as a commutator, sorry, p. Okay, and the right, and then plus, okay, so and then plus gradient of dt p equal to 0, right? But I will move plus gradient p to dp 0 to the right-hand side. Okay, so that's really the Ararian version of what we have just done, right? So we have been doing it on the boundary and using the, using the boundary integrals, okay? But instead, you can just do it directly to the Euler equation, just taking a material derivative, just like that, okay? And restrict it to the boundary, okay? And that's exactly the equation, because if you look carefully, I will not calculate for you. So this exactly is minus gradient P dot gradient V, okay, dot gradient V. But, and in the case of the irrotational, that's really just minus dp dn times the, how do you say that? The derivation normal operator, okay. That's where, that's exactly, so this is exactly the, and then remember our A is negative dp dn divided by the length, right? So this is exactly, so this exactly is the equation ZTT, okay, so ZT bar, two derivative, of course, you bar or not, it doesn't really matter. So IA the alpha, that's really this operator, okay. And the right-hand side is minus AT Z alpha, right? So remember, of course, there is a bar, but this is pointing in the normal direction, okay? So this is because dTp equal to 0 on the boundary of omega, because if the pressure is 0 on the boundary, and if you take a material derivative along the boundary, it will not change the boundary value. So the boundary value is still 0. So this is pointing in the normal direction, okay? So this quantity points in the normal direction, okay? This is really just the quantity minus IAT C alpha, of course, with a bar, if you look at this version, okay. Okay, so now this is introduction, so motivates the thinking, right? So instead, and this is actually a very convenient framework, because in this form, so if you look at the boundary integral, it looks like you can only work on Waterway. But if you just look at this Aurarian version, and you suddenly realize you can do a lot more things, right? Many free boundary problems can be solved. So in fact, after Christou Limbara's paper, and there was many work following that framework. Okay. So let me just briefly summarize this, right? So the Newtonian free boundary problem. So here we just write the corresponding, so incompressible irrotational, and this is a material derivative connected gradient P. So we are just using the model that the Christou Limbara was talking about without gravity, and the pressure equals 0 on the boundary, and this is the particle moves along the boundary. And in this model, the Taylor-Sine condition holds automatically by Hoppe's maximum principle. Okay. And of course, the idea is that reducing the problem, so like what I said, reducing the problem to the boundary, right? So that's for the Waterway, okay, for the Newtonian version, okay. And then the key idea is, after differentiating the momentum equation with respect to the material derivative, we obtain a quasi-linear equation, okay. The quasi-linear equation exactly looks like this, okay. And also that, okay, so, and of course, it's incompressible irrotational, so the velocity field is satisfied the Laplace equation, okay. So here, that the gradient here is the derivation normal operator, okay. A is negative dp dn, okay, like, you know, that's the commutator, okay. So what we did is just using boundary integrals, okay, and we are able to, and what's most important is that the first equation is a quasi-linear, okay. And the reason it's a quasi-linear, not only it's a quasi-linear, but it's also of hyperbolic type. Okay, so why it's important of hyperbolic type? Because we know that if it's elliptic type, Cauchy problem is ill-posed, right? So we need it hyperbolic. The reason it's hyperbolic is because we have A positive, right? Because this is A is negative dp dn, okay. And the second is derivation normal operator. The derivation normal operator is non-negative, okay. This is because of we know that because this is a Green's identity, right? So derivation normal operator on the boundary, okay, of a domain, always equal to the gradient of U squared. This is a Green's formula, okay. So that's positive, okay. So this guarantees the positivity of the second term, and then we have a hyperbolic type quasi-linear equation, and then the usual method of solving hyperbolic equation applies, right? So you just use the energy method, okay? And we proved well-posedness. Okay, so this is what Christopher Limbara did. Okay, so Christopher Limbara, of course, they want to work with non-zero vorticity, so they cannot, boundary integral is not convenient. So what they do, they say that instead of using boundary integral, they just write down the elliptic equation for the pressure and dTp, right? So because you see, we have to have an equation for the left-hand side, the right-hand side. Okay, so this is, we have to know what is really the governing equation for the coefficient A and for this. Okay, A is negative dpdn. So you just write down elliptic equation, the equation. Okay, and we know it's 0 on the boundary because this is the assumption, and this is because this is a consequence because the particle on the boundary remain on the boundary, and this dt is a material derivative. Okay, okay, and then they say, then they use the ellipticity, okay, the elliptic estimate to recover the estimates. Okay, so now I want to mention here, there's a crucial thing. Okay, so you can say that, well, we can say that, okay, let's just solve this equation, right? We can solve this equation, but in the domain. So write down instead of on the boundary. So there is really an advantage of working on the boundary because then taking derivative become very natural, right? So you just taking derivative with respect to parameter alpha, okay? But so now you are solving the equation inside a moving domain. So but we know that to get a Pauli estimate, we have a lot of times we have to take higher derivatives, okay? So how do we take higher derivatives? So what they do is, so this becomes awkward, right? So if you take a spatial derivative, the P is not 0 anymore on the boundary. Actually, what is the spatial derivative P? We don't really know what it is on the boundary, right? So you cannot really, so you can take spatial derivative to these two equations, but you won't know the boundary value, okay, of these quantities. So what they do is that they still take spatial derivative, but they just separate the domain into two. One is in the interior, one is on the boundary. So on the boundary, they only take the tangential derivative, okay? So, and then they try to put them together. So near the boundary, they don't want to, you don't want to touch the normal derivative, okay? Cut off in the normal direction, okay? So with this, they obtained a Pauli estimate, and with their method of treating higher order energy. And it took a while for Limbara to find existence used in Nash-Morse iteration. So this actually, I would say that, okay, so this is what they did. Okay, so now we go back to the hard phase model, right? So hard phase model, if you look carefully, it's very similar to the Newtonian model, right? At least formally, it's very similar. So let's see, yeah. So this one, so this one looks like the Euler equation, right? So if you think, so here we want to say that, well, this is our material derivative. We call this dV, okay? dVV, and plus gradient of rho squares, like half rho squares like P, okay? P equals 0 on the boundary, P greater than 0 in the interior, incompressible irrotational, okay? Okay, so now we want to just also do the same thing, okay? So we do the same thing. So at least because when you have no idea how to start, so you do something, just follow some idea that's already there, right? Okay, so now this is the, okay, so, sorry, okay. So N is outward uninormal to the domain, okay? So again, that because P is sorry, P. Sigma is 1 on the boundary, so gradient. So this gradient is not this is a full gradient, okay? It has a time direction. So this is parallel to the normal direction. So we just using the same notation as the Waterway. So we write like -AN, okay? So A is a positive because the A is positive because of the Taylor sign condition we assume initially. So A0, 0 is a time, okay? 0, so at initial time, okay. And we write this, we call this the material derivative, okay. We call this. So we're differentiating this equation by dV, and we get this formula. And this you can calculate, exactly give you A times this is really the hyperbolic derivation norming operator, okay. And now we got this equation, okay. So we got this equation, formally look very similar to the Newtonian case, but there's a crucial difference, okay. So, and we also have that, of course, the velocity field will satisfy the D'Alembert equation, okay, instead of the Laplace, okay. So, and we know that the hyperbolic and the elliptic is very different, right? Satisfy D'Alembert, Laplace equals 0 or box equals 0 is something, has some fundamental difference. And what's crucially different is that it's not very clear whether this derivation Neumann operator, hyperbolic derivation Neumann operator is still positive. And we know that's crucially important, right? If this is negative, then its elliptic equation, the Cauchy problem will make no sense, okay? Will be opposed. Because we already assume this A is strictly positive in initial time. So we know that if the solution exists, then it will remain positive for a short time, okay? So we don't worry about A, okay? For a short, because we're solving for a short time, we can say A is positive. But one first question to be asked is whether this is a positive operator, okay? And we can also find the equation for sigma, okay? And of course, sigma equals 0 on the boundary. And the equation for the box of sigma, derivative of sigma, and the material derivative of sigma is also 0 on the boundary, okay? And that's very, very helpful, okay? So the question is whether this hyperbolic derivation Neumann operator is positive, okay? And is this the right-hand side still lower order, right? How do we control it? Because this equation now is controlled by the box equation, not the Laplace equation, okay? And there's no way to have a boundary integral formula. So we don't have boundary integral formula to get any idea, okay? Okay, so now here is the main ingredient, okay, of the proof. So we show that actually this is positive. Okay, so this is really the most important step, I would say. That's the hyperbolic derivation. So I'm going to give you some idea how this is done. Okay, so I'm going too slow, looks like. Okay, okay. So then also the coefficient A and the right-hand side are of lower order. So that's great news. So that we are having a quasi-linear equation of the hyperbolic type. Okay, and so we can get a Pauli estimate, but there's a crucial new thing we introduced to do the higher order energy. Okay, instead of doing tangential derivative, like what I said, it would be awkward because we don't really know what is the derivative. So sorry, instead of doing the spatial derivative, I should say spatial derivatives, right? So spatial, if I take a spatial derivative to sigma square, I won't really know what's its boundary value. Okay, but if I take a dV derivative, material derivative to sigma, I can take as many as I want. I still have its boundary value equals to 0. Okay, so the boundary value of all the higher derivative, the material derivative to sigma square has boundary value equals 0, right? So that's, and that's, of course, getting the governing equation inside domain is not so difficult. You involve some commutators, right? So you just apply the, getting the higher equation is okay because you just keep applying the dvk and then you do a commutator, you can find the equation, right? So, but the boundary value is not easy to determine, but this quantity do have 0 boundary value, okay? So we use the material derivative to get higher order energy, but if as all of us have done a Pauli estimate, we have to also a lot of times use the Sobolev embedding. So that means we still need to know the Sobolev norm of the solution. So how do we get to the Sobolev norm of the solution? And we use equation to show that dv square 2 material derivatives equivalent to one spatial derivative. Why is that? Again, this is because here, right? Because here, the left-hand side is higher order term. This is higher order term, and this is 2 material derivative. So here we have 2 material derivative. Here we have 1 spatial derivative. So 2 material is equivalent to 1 spatial derivative. Okay. So, and you can show that. Okay. So use the equation, we can show these two are equivalent. Then the control of the material derivative translates to control of the two material derivative translate to one spatial derivative, and this allows us to control the L infinity norm. Okay. And we do have to, because box do not have elliptic type estimate. Okay. Now, just because of this property, we also have that box equal to elliptic operator plus some lower order term. So why is that? Because box is dt squared minus Laplace, right? Laplace is elliptic, but dt squared is, you can roughly think dt squared is like dv squared, okay, plus some error. So but dt squared is like a lower order, right? Because dv squared is lower order. dv squared is like 1 dx, okay? So therefore, we will also have, so we can also employ elliptic estimate. So all things put together, so this works very well and also suggests a very natural method of constructing the solution. So we just use Galerkin method, discretize the equation, okay, using based on some orthonormal basis, right? So with eigenfunctions. And then you just, and you can also construct your approximating equation so that obeys a similar type, same type of a priori estimate as your, as your original equation, the full equation. And then you can show uniform boundedness of the solution, the approximating sequence, and then you converge. Okay, so then that's how it's done. Okay, I have 3 minutes. Okay, am I? Time goes fast. Okay, sorry. This is the first time I speak about this, so I thought I have plenty of time. Organization. Okay, so what is the main idea of proving the positivity? Okay, so the key, of course, is because to treat nonlinear equation, the key is really, one of the key ideas is just really just finding the right multiplier, right, to study. Okay, so finding the right multiplier to get your estimate. So of course, we already know that supposedly this is a quasi-linear. Then the natural thing to do is you just multiply this quantity and then you integrate, right? So we multiply this quantity to the equation and we integrate, and turns out that we can find that it all work fine. So the right-hand side, the left-hand side is a positive energy. Okay, so
here, could you speed up, please? Because there's another lecture in a few minutes.
Yeah, speed up. I'm finishing. Okay.
Thank you.
So I think I'm finishing in 1 minute. Okay. So the idea is really just okay, finding the right multiplier. So I will not really talk about this, and then I think that, and then you can finding, so lower order term. So to prove the right hand side is lower order is also finding another good multiplier, and then to show it's lower order. Okay, so this is really the basic idea, right? So we also have Newtonian limit, just by say, so to study Newtonian limit, we have to introduce the speed of light. Okay, so it's not c equal to 1, but c, a general c, right? So everything is just put back. So we put c back into the equation, and we have to find, so we find that so that's the equation we deal with, right? And we look at the rescaled quantity, okay, and we show that this rescaled quantity is uniformly bounded with respect to c. So it has a priori estimate independent of the speed of light, so we can pass to the limit. Okay, and when you pass to the limit, okay, we prove a priori estimate independent of c, and then we show that the rescaled solution goes to the solution of the Newtonian equation. Okay, as time goes to, as the speed of light goes to infinity, the relativistic solution converge to the Newtonian solution. So, thank you.
Thank you, Sijue. Is there a quick question? I have a question. So this is supposed to model a collapsing core of a star.
Okay.
So is the boundary that you're talking about roughly like a collapsing star boundary?
I don't know. To be honest, no, I think that, no, no, I don't know how to answer this.
Do you have any restrictions on are there basic restrictions on the shape of the boundary?
No, it's just
Any domain.
No, it's just any domain, any domain.
You start with some boundary at time 0 and then you solve for a little bit.
That's right. Then you start with time 0. At time 0, that's you know, whatever a bulk of fluid, right? And then you let it can just flow freely for a short time. You can just build a solution for a short time. So I'm just trying to explain this model, why this is physical. That's it. Okay. But the physical relevance of thinking about stiff fluid, that's all. But whether this model degenerate, you know, a massive star, that I don't know. Okay, so actually there are many related questions to that, like phase transitions. Okay, but this is another type of free boundary, right? So how do you? Okay.
I think you're right. There are many big questions that can be asked about this kind of problem.
Yeah, but this, you can think this is like, try to study a model equation, try to get some basic understanding how to solve a problem, a one-phase problem, right? Just some fluid, relativistic fluid bounded by some vacuum outside. It's a one ideal fluid. But okay, yeah. But of course, like I mentioned, that this applies to general barotropic fluid as well. So if thinking speed of light equal to sound speed is too much, it does apply to general. Yeah. General.
Thank you, Sijue. Thank you very much.